Hello and welcome. My name is Brigu and this is my presentation on the various RAID levels. So let's get started. RAID is also defined as a redundant array of inexpensive disks or redundant array of independent disks. The previous terminology used the term inexpensive, while the contemporary terminology uses the term independent. So in layman's term, RAID is just a way of arranging multiple disks that are viewed as a single disk or single logical disk by your operating system. So the first question that comes to your mind is, why would we need RAID, right? We can have a single disk that can have all our data, but why do we need RAID? What you need to understand is, when you're reading a particular data from the disk and you have multiple requests coming in, those requests can only be serviced one after the other. That means that the time it takes to service that request will depend on the number of tasks that are available. Now, if we divide these tasks into various disks and these disks can be accessed parallelly, then you can save on time and your disk can become, or a disk function can become really fast. First reason is parallelization. The second reason here is that the additional number of disks act as redundant disks. For example, if you're running a really important company and you cannot afford to lose your data, but your disk fails, what do? You cannot recover it back. But using redundant disks or copying your data on other disks ensure that you can never lose your data, and if ever you lose your data, you get it back, right? So these are the various levels of RAID, starting from level 0 to level 6, which are the common levels, while level 10 is a special characteristic of RAID, which is the nested level properties. An important thing to note before we proceed is that these levels do not signify a particular hierarchy, but are only indicative of different architectures that exist. Let us look at some characteristics of RAID. There are three primary characteristics of RAID. Firstly, that this is a set of disks that is viewed as a single logical disk by the operating system. Secondly, the data is distributed across various physical disks in an array scheme that is known as striping. I'll explain what striping is in the very next slide and why it is important to RAID. Thirdly, that the redundant disk capacity is used to store parity information. That means that you have a disk which does not store your data, but only stores parity information that is calculated on the basis of various codes, such as Hamming code or cyclic code such as CRC, which stores the parity information in case your data is lost. You can get it back using the parity calculations which are involved. I'll explain some of the parity calculations later in various RAID levels as and when they are pertinent. But something that is important to note here is that the details of the second and third characteristic vary from level to level, right? That means that they can have their own independent schemes and how they stripe the data, which we'll also see when we come to those levels. But the second thing to note is that level 0 and 1 do not exhibit the third characteristic. I'll explain why. In the truest sense, they're only honorary members of the RAID cycle, but are not actual members of the RAID cycle, and they do not exhibit the redundant characteristics. So let's move on. So now let's understand what striping is. The logical disk is divided into various strips, as we can see, from strip 0 to strip 15. Now you have a way to arrange these disks in any manner possible. The way you do it here is that you have strip 0, strip 1, strip 2, strip 3 in a sequential manner. But why do you want it in a sequential manner? The simple answer to this is, for example, if you're running any program or any game, let's take an example of a game that you're running. The calculations of the amount of data that you need to access will be available in a sequential manner. That means that if you have to access storage location 0, it is more likely that you'll have to access a storage location 1, 2, 3 as well, because the program will run in a sequential manner. That means that you'll not have any lag, or the time it takes for you to get the data into the cache or RAM is lesser than it would have been if the data was arranged as a single disk like this. This means that striping can save on a lot of time and also can help you retrieve your data faster, which means that striping is extremely important. How striping is managed is it is managed by an array management software that can vary from various RAID levels, and we'll see some of them are complex, some of them are easy to maintain. This depends totally on the architecture and the kind of thing that you're trying to execute. So let's come to RAID level 0. RAID level 0 is not a true member of the RAID family, but it is only there as an honorary member because it exhibits some of the characteristics of RAID, right? What are these? And let's understand with the help of this diagram, right? So your data is divided into two disks, disk 0 and disk 1, and A1, A2, A3, A4 are sub disks, or like you consider as smaller stripes in these cases. So now, like I discussed previously with the game example, if you want to access a data which is sequentially arranged, you can save on time by using RAID 0. But you might wonder that where is RAID 0 ever applicable? So there are only few applications such as supercomputers or other applications that require fast processing and do not care about data storage and data loss, and hence you can have fast processing via RAID 0. right? So let's look at some advantages and disadvantages and applications of RAID 0. The first advantage of RAID 0 is that input-output performance is greatly improved by spreading the input-output across various disks. There is no parity calculation involved, and hence you save on time. It's a very simple design and it's very easy to implement, hence that counts as a bonus. The disadvantage is that the failure of just one drive will result in an array of data being lost and you can never recover it back. That is RAID level 0's disadvantages. Right, the application of RAID level 0 could, as I've told you earlier, could be extreme processing where you require extreme amount of processing such as supercomputers, but also applications like video production, editing, and any application that requires high amounts of bandwidth, you can use RAID 0. So let's move on to RAID 1 now, right? So RAID 1 is an improvement on RAID 0 or a slight modification on RAID 0, and it incorporates the term redundancy, but not in its truest sense, right? Because the only way you have redundancy over here is by copying the entire contents of disk 0 to disk 1. That means the significant disadvantage on the face value, as you and I can both see, that if you have a disk of say 2 terabytes, only 1 terabyte is usable by the user of that disk. That means that you lose at least 50% of your disk in storing the data again. So let us look at the working of RAID level 1. So for example, if I have to service a read or a write request out of like 2 disks that are available, disk 0 and disk 1, and my data is available on A1, then which A1 do I select? The A1 that I select is dependent upon the minimum seek time plus the minimum rotational latency, and I service the request from there. But what happens after that? After that, to ensure that both A1s in disk 0 and disk 1 have the same amount of data or the same version of the data, we have to update the other disk. But this disk can be updated in parallel and hence doesn't slow down the entire process. So the speed of updation of the disk depends upon the slower of the 2 disks. Right? So let's understand in a scenario what happens if say A2 of disk 0 fails. Then I take out the faulty disk, I put in the new disk, and A2 of disk 1 copies the entire data into disk 0 A2 and we get the data back. Right? So this is how RAID level 1 works. Now let's look at some advantages, disadvantages, and applications. Right? So the advantage is obviously being that there is 100% redundancy of data, means that there is no rebuild necessary in case of a failure. For example, like you don't have to calculate any code or you don't have to waste time on it, just copy all your data back and you get your data back, right? Secondly, in certain circumstances, you can sustain multiple drives failure. What do I mean by this? For example, I can have this A1 failing, this A2 failing, this A3 and this A4 failing, and yet my device would be operational and you would not need to shut down your entire system to make sure that there are changes. All these things can be copied in parallel and you can ensure that your function still happens, right? The third advantage is it is the simplest storage subsystem design, right? Out of everything that we're going to see in the future, this is the simplest model that we have on our hands. But what are the disadvantages? Firstly, this has the highest disk overhead, and secondly, you lose a lot of data or you lose a lot of disk space when you implement RAID 1 systems, which might not be ideal. Right? So what are the applications of such a system? And you obviously want to apply this in a system which needs a lot of data redundancy. That means that you cannot afford to lose that data and you have to get it back in any case. So things like applications around accounting, payroll, financial applications, or any application that requires a very high amount of reliability is extremely suitable for RAID level 1. So let's go on to RAID level 2, right? In RAID level 2, there is a parity disk that exists, right? And there's certain special characteristics of RAID level 2 and 3. Firstly, the first condition being that all the disks have to spin in an order where they have to be synchronized or in sync with each other. That means that they have to have be at a similar place to make sure that you can perform operations on them. And the amount of data that you can stripe is limited in RAID level 2 and 3 and could be just a bit, a byte, or even a word. It isn't that large, right? So typically a Hamming code is used to detect and correct a single bit error, and Hamming code can also detect a multi-bit error but cannot correct it, and hence those things are used in RAID level 2. These are the parity disks, as you can see over here, which are labeled with a subtext P. These are the parity disks that you use, right? So what are the amount of parity disks that you need? The amount of parity disks that you need is proportional to the log of the number of total disks that you're having, which can be huge when you implement a huge RAID 2 level system, right? So let us see the advantages and disadvantages. Firstly, extremely high data rates are possible with RAID level 2. Secondly, the higher the disk transfer rate required, the better the ratio of the error code correction disk. Thirdly, it has a relatively simple controller design as compared to level 3, 4 and 5, which can be an advantage over here. But the disadvantage is that there is an extreme high ratio of data disks involved with smaller word sizes. That means that you have to have a log of n of total number of disks as your redundant disk. That means when you have a large application or you're building a large database for a company or a software, you cannot have, or you spend a lot of money on redundant disks that you might not want to do, and you can have better techniques like RAID 3, 4 and 5, which we're going to discuss in detail later, and those applications are more suited to you. Secondly, there's inefficient entry level cost. Why? Because all the disks have to be synchronized with one another. That means the amount of parallelization that you can do with RAID level 2 is severely limited to a point where the spindles have to be in sync with each other, right? RAID 2 would only be useful in an environment where many disk failures occur. But given the modern disks, they have a built-in mechanism or certain built-in mechanisms that have only, say, one read error per like 12 terabytes. So the amount of reliability that we can receive from the disks is also like sufficient to a certain extent, and hence you do not need to rely on RAID level 2. Having considered all of this and seeing that the disadvantages and the costs are too high as compared to the advantages, we see no commercial implementation that exists right now, or this is not commercially feasible. So let's move on to an improvement on RAID level 2, which we know as RAID level 3. RAID level 3 involves a byte level striping, right? In byte level striping, you have the stripes that are allocated as per 1 byte each. But the advantage of this disk is that no matter how many disks you have, unlike say you want to have a log of the total number of disks in RAID level 2, here you only need a one disk to ensure that you have adequate amount of redundancy that you can achieve, right? Which makes the process even faster. Now, how do we achieve this redundancy? This redundancy is achieved through the process of parity correction that we saw in Hamming code, previously also in our lectures and what we have studied in our syllabus. So let's consider an example. Right? Here's an example that we're going to consider. We're considering an array of 5 drives, x0 to x3, which contain data, and x4 being the parity disk. Right? So now this is the equation that we're going to follow, that where x4 equal to x3i, XOR of x2i, XOR of x1i, XOR of x0i. Right? Where XOR is the exclusive OR function. Suppose we say this disk fails. Now what happens? Right? Now over here, what we're going to do is we're going to add x4 and x1 to both sides. So what does this mean? If I add x4 over here, that means x4 plus x4 becomes 0, since any XOR calculations involving two of the same type make it a 0, and I have only x1 on the left side. Over here on the right, when I have 2 of x1, because I've added x1 and x4, I make this term to be 0 and I add another x4, and hence I get this equation. That means that if my drive x1 is to fail, this is how I get my x1 back, and this is how RAID level 3 essentially works. Right? So let's look at certain advantages and disadvantages of RAID level 3 along with certain applications, right? So you have an extremely high read and write transfer date. The disk failure has an insignificant impact on the throughput because you can adequately get it back on time. There's a low ratio of error correcting code parity disks to data disk. That means high efficiency. As I told you, you only need one disk for n number of disks that you're having with your like application or the database that you're trying to build. RAID level 3 has its own set of disadvantages. Firstly, the transaction rate is equal to a single disk drive at best. That means that if all disks have to be like synchronized at a point, that means that they cannot perform the entire function in parallel, and you have severe restrictions on the amount of functions that they can perform, which is a significant disadvantage of RAID level 3. But also the controller design can be fairly complex as compared to RAID level 0, 1 and 2. That means that RAID level 3 is a bit more complex to actually achieve. But what are the applications over here? Again, applications like video production, live streaming, image editing, video editing, and any application requiring high throughput can be processed adequately with RAID level 3. So let's look at RAID level 4. RAID level 4 uses the block level striping technique. As we saw in RAID level 2 and 3, which used a smaller amount of striping data, RAID level 4 uses significantly large amount of data which uses a block. That means that you can have more amount of data in a particular stripe in RAID level 4. But the second advantage, or like the second great feature about RAID level 4 that is a improvement on RAID level 3, is that RAID level 4 through 6 use independent access technique. As we saw in RAID level 2 and 3 that all the spindles had to be synchronized to a point, RAID level 4 doesn't require you to do that. What RAID level 4 needs is that you have a single parity disk and all the disks can be obtained or can be used in parallel, and the function's result can be obtained in parallel, and you do not have to have a synchronization amongst the disk, right? So a bit by bit parity strip is calculated across corresponding strips on each data disk, and parity bits are stored on corresponding strip on the parity disk, right? But here, RAID level 4 involves a significant amount of write penalty, because each time a read or a write operation is performed or a write request is performed, you need 2 amounts of reads and 2 amounts of write to write to the parity disk, and you have to update that disk over and over again, right? So now let's demonstrate why this is the case, right? So let us again consider a disk of 5 drives that has X0 to X3 and contains X4 as the parity disk, right? So these are the calculations. Assume that this is our relationship, right? X4 equal to X3s or X2s or X1s or X0. After the update, there are potentially altered bits. For example, you've altered X1 and now you've also altered X4 as a result because X1 has been altered. So what do? Here, you add X1 plus X1, and X1 plus X1 is 0 again. So there is no difference to the equation on either side. Hence, you add it to the right hand side as well as the left hand side, and you won't make a difference on the left hand side. Now, for the sake of convenience, what you do is you add X1, you replace this X1 and this X1, and you swap them out basically, and you get this equation, X3 plus X2 plus X1 plus X0, which is nothing but X4 as we've seen from here, and hence we put it as X4. And the second thing that you do is that you have an X1 not here, and you put an X1 not here, and there's an X1 over here. That means that when you have to calculate the new parity, the software management has to have 2 reads on X1 and then 2 writes on X1 as well to ensure that you have the correct amount of parity. That means that RAID level 4 can suffer from a great amount of write penalty, which might not be ideal. Having that said, RAID level 4 is still a much more of an improvement on RAID level 3, and there can be certain advantages, disadvantages that we can see over here. The advantages are that there are extremely high data transaction rate. There is low ratio of error correction disks to data disks, that means high efficiency. Again, as RAID level 3 had it, only 1 disk required. But the disadvantages here outweigh the advantages that we can receive from RAID level 4. Why? The controller design is quite complex. That's the worst write transaction rate and worst aggregate transfer rate that we have in RAID level 4. Again, as I've told you, you need 2 writes and 2 reads to have 1 change, which is not ideal for any disk whatsoever, especially with applications that require great amounts of reads and writes, as we saw financial software in the earlier slides, right? Again, there's also difficult and inefficient data rebuild in event of a disk failure. That means that you have to refer to 2 other data and calculate that, which requires a lot of time. Alright, so every write operation requires a parity disk, which means that there can be a bottleneck situation. That means that if multiple disks are operating at the same point of time, all of them need the parity disk and they have to operate the parity disk right now. But this can only happen in a sequential manner because again the parity disk is being used for another data, which means that you always slow down RAID level 4, and which may not be the most optimum or efficient in any case. And you can have a severe bottleneck situation, as I've explained to you over here. Since the disadvantages outweigh the advantages, nobody really uses RAID level 4 in today's time, and there is no commercial implementation or viable applications that exist for the same. So let's look at RAID level 5. RAID level 5 is organized in a similar fashion to RAID level 2. However, if you notice certain subtle differences, again, you have 4 disks that are arranged, but the parity disks are arranged on independent disks and are not on the same disks. That means, so for example, the parity disk D is on disk 0, parity disk C is on disk 1, parity disk B is on disk 2, and parity disk 3 is on parity disk A is on disk 3. Right? That means that the bottleneck situation that we saw earlier is avoided, because even if all disks are operating a read or write, they can update the parity disks in parallel, and that means that you cannot ever have a bottleneck situation that occurs previously in case of RAID 4, which is a significant advantage in the case of RAID 5. Let's look at advantages, disadvantages, and applications of RAID level 5. First advantage is that there's a highest read data transaction rate. There's low ratio of error correction to disks. That means that you can adequately use disk and save on costs as well, which is something that was common in RAID level 4 and RAID level 3 as well. Disadvantages being, obviously, as you implement a bigger or a complex design, you have to have a more complex controller to control that design, and you have to have a complex amount of scheme to rebuild the data in case of a data loss, and that is a disadvantage. Having that said, RAID level 5 is still better than RAID level 4 in terms of performance and is extremely marketable and is, or like currently was, the industry standard for building RAID disks, right? So the applications being file and application servers, database servers, emails, intranet servers, and this is the most versatile RAID level that you see. As I've told you, it was the industry standard at some point, right? So let's look at the last thing that is a conventional RAID level, which is RAID level 6. So let's look at RAID level 6. RAID level 6 was introduced as an advantage or a subsequent like improvement on RAID level 5, where the only subtle difference with RAID level 5 is that the amount of parity disks that you need is increased by 1. That means that there will be 2 of D parity disks, 2 of E parity disks, 2 of C parity disks, 2 of B parity disks, and 2 of A parity disks. This means that you have increased amount of reliability and the total amount of disks that you require is n plus 2. All these disks, and you can easily regenerate the data from all these disks given that they fail within the mean time to repair. That means, for example, if one disk fails, the second disk does not fail in the mean time to repair. Secondly, there is a substantial write penalty to all these disks having to overwrite 2 disks. There exists obviously a substantial write level penalty in RAID level 6. So let's look at the advantages and disadvantages of RAID level 6 for a minute, right? Advantage is that it has an extremely high data fault tolerance rate and it can sustain multiple drives failure. That means that for example, this drive can fail, say this drive can fail, this drive can fail, and yet your program can continue without a hitch because there is another drive that is covering it, right? But the disadvantages are also there, right? For example, there is an extremely complex controller design, overhead to compute parity is large, which may not be ideal in all applications. But what is the ideal application for this case? Firstly, in situations that are extremely hard real-time systems, you can use this. A good example that comes to my mind is, for example, a space shuttle launch. You cannot afford to miss even a single bit in a space shuttle launch because even a single bit can lead to the crash of that extremely high hydrogen powered fueled rocket, which could cause damage to life, property, as well as failing of the entire mission. And you need extreme amount of reliability there, and you'd probably use RAID level 6 to use that. When I was researching of what RAID level to use, people always suggested that you go for RAID level 6 over RAID level 5. And I couldn't see the significant difference and why I would choose something that requires an extreme amount of write penalty over something that is far easier to implement and was the industry standard. I just didn't get it, right? So I inquired, and this is what I found. And this is interesting, and I'll explain it to you through an example which might tell you of why it is important to use RAID level 6 in the current scenario. So the current data drives that are manufactured have read errors every 1 in 10 raised to power 14 bit. That means that you can have a read error which is at an average of once per every 12 terabytes of data. Now assume that you're a large company or a company that requires their data to be safe and secure. So for the purpose of this example, you have 14 terabytes of data which is split across 7 disks, and these disks are of 2 terabytes each. Now let's assume one fails due to a hardware error or some other error and you cannot use it for the time being, but you also have to use the other disks. That means that you have 7 disks now, out of which one fails, and you have 6 disks, which means that you have 12 terabytes of data. You try to read all those disks in a serial manner, and assuming a read error occurs, because it can occur at an average in once every 10 raised to power 14 bits. So the entire data becomes useless because you cannot recover it, because the other disk has also now been rendered useless. That means your entire data of 14 terabytes is now compromised to an extent that you cannot get it back. What would happen if we had used a RAID level 6? The amount of disks that would need to fail, or the amount of read levels that I had with an additional disk, would be larger. That means that 14 terabytes of data wouldn't be enough to corrupt my entire system, or my entire system wouldn't be brought to its knees because of 14 terabytes of data. The amount would be much more larger than this. But sooner, RAID level 6 will also become obsolete, because the amount of data that we're generating day by day is in terabytes itself, and you require, big companies might have, like Google, might have petabytes of data on their servers, and they require some other technique, or at least ensure that the data does not fail. Hence, at least for the purpose of our example of our study, we think that RAID level 6 is much more reliable and is needed as the industry standard, or until something better comes up, over RAID level 5, right? Let's move to the last part of this presentation, which is about nested RAID levels. Nested RAID levels is not in our syllabus, but yet like a lot of applications do exist for nested RAID levels, and one example of this is RAID level 10 or RAID level 1 plus 0 or 0 plus 1 as you like to put it. So what is RAID level 10? It's a combination of RAID level 0, that means that you have like disks in sequential manner over here, as on also RAID level 1, that means that you have 2 of A1 over here, 2 of A2 over here, and you preserve this. There are specific applications where you would require this. Here, an application that requires great amounts of speed as well as great amounts of reliability can use RAID level 1 plus 0. An important thing to note is this is not the only modification that people have tried with RAID levels. People have also tried RAID 50, which is RAID 5 plus 0, RAID 60, 6 plus 0, RAID 100, which is RAID 1 plus 0 plus RAID level 0, which is also an improvement of various levels. The choice of RAID levels obviously depends upon the kind of application that you want to use and the amount of throughput and the energy that you can spend, on your application, and that is completely left up to the company and like what is profitable to them, right? Here are the list of references that I used while creating this presentation. Obviously, YouTube videos were a great help in helping me understand the concepts much better, but William Stallings gave me the basics and fundamentals of what RAID is. Wikipedia also played its part with like the pictorial representation of RAID levels accurately and helped me prepare this presentation. I hope you learned something from this presentation, and I hope I could give you the basics or the primer of RAID levels, and I hope to see you again next time. Thank you.